All right, this video is going to talk about a simple application of sines and cosines. It's called simple harmonic motion. Simple harmonic motion. And simple harmonic motion basically says that the distance d from the origin, or basically from the x-axis, as we would kind of imagine it, right, where we would start from, right, at a given time t, is given by either the sine or the cosine here, depending on if you want to start at a maximum, a minimum, or right on equilibrium, right? And we're thinking about these graphs, where a and w are real numbers, right? Where a would be, again, the measure of the amplitude. So again, a would measure how high or how low we might go. And w, on the other hand, is sort of helpful in that measurement of what we call the period, and also applies to the frequency. We'll talk about that in a second here. But again, harmonic motion basically saying, if we have something on a spring that's measured, it might get pulled upward, and then it would drop back down due to gravity, but the spring would pull it back up. And it's going to repeat that pattern, over and over and over again. So again, the distance d from the origin at a time t, right? That time t essentially is going to be our axis here, and d, again, it would be kind of like the y value. It would be our measurement up or down from that x-axis. The period is the time it takes to complete one full cycle. So again, the time from beginning to when it would repeat itself. So we might say that this, here would be measure of the period, or we can go from max to max, or we can go from minimum to minimum. But again, one full period before it repeats itself. The amplitude, as we already talked about, is again half the total height. It's going to be the distance from the origin or the x-axis up to the top or down to the bottom. And the frequency is actually the number of cycles per second. So let's say that this was a measure of 1 second here in time, right, t. Well, how many periods did we essentially complete, right? How many full cycles did we complete before that happened? It's not the distance of the period. Remember, the period is how long it takes in general just to repeat itself one time, right? Whereas the frequency is how many of those repetitions happen in a given amount of time. The nice relationship there is that the frequency is actually just the reciprocal of the period. So again, if 2 pi over w for us right now, what we often call b in a larger equation, but 2 pi over w is equal to the period, well, w over 2 pi is actually equal to the frequency, right? Very simply. So it's just the reciprocal there. Let's just look at a couple of simple examples. Again, we've got a spring attached to a block down here. And again, if you pull that block downwards, right, the spring's just going to pull that block back up. But again, as the spring pulls, it's probably going to create a little momentum. It's going to pull it up a little bit more, right? So now the spring's got to go from here back to equilibrium. And then all of a sudden, gravity, of course, isn't just going to stop it there. It's going to let it go down a little bit more, right? So again, our spring's going to continue to rise and fall and just repeat that pattern over and over and over again. Now, we have to say we're measuring that over time, because basically remember that, again, we're not measuring it where our actual measurements are just up and down. We're not going side to side at all. But again, our graph is going to say, well, hey, if I pull that up to the top, right, or we pull it down to the bottom, as we showed in the example, it's going to rise to the top, and then it's going to fall back down again to the bottom, right, and keep on continuing that pattern as we go. What's the maximum displacement of this block? Well, that would depend on how far down we pulled or how high it rises. Basically, that's going to be our amplitude. Maximum displacement is another way to say amplitude. Well, for us, since a is 4 out in front here, basically we would say that that's 4 either inches or centimeters or whatever distance we're pulling that, right? They didn't really give us a measurement, but our maximum displacement would be 4, right? We're going 4 up or 4 down from the middle, right? From equilibrium. What's the period? Well, remember that period is just 2 pi divided by b or w, depending on what we call it. It would be that 8 pi in there. So the period of our graph right now, cancel the pi's, would be 1/4. Right? 1/4 of our time measurement, essentially. And what's the frequency? Well, remember we said the frequency is just the reciprocal of the period. So it just so happens that the frequency for us would be 4 over 1, or basically 4 cycles, right, in whatever length of time we're looking at. Right? The frequency would have been 4 full cycles over whatever that length of time would be. Let's look at one more example real quick. A point at the end of a tuning fork moves in simple harmonic motion, right? If you're familiar with a tuning fork, right, it's going to wobble, right? When you hit it, it's going to be just shaking there. But that point at the end of the fork is going to go back and forth, right? It's going to be shaking. Find W, given that a tuning fork for middle C has a frequency of 264 vibrations per second. So again, they're not asking us anything about A or D for that matter. What they're really asking us just to do is find that W. Well, remember that W is equal to 2 pi over the period. And if the frequency is 264, right, vibrations per second, the period is going to be 1 over 264 seconds per vibration. Right? We're just flipping that over. So now we can go back to our W and say, well, 2 pi divided by 1 over 264, multiply by the reciprocal of our fraction here, right, toward the top, and W will equal, well, 264 times 2 pi, or basically 528 pi, right, will essentially be our W. And again, it's just a measurement. It's going to be a number put into an equation, so we don't really need to provide a label there. But again, our W value would be 528 pi. I hope that helps you with simple harmonic motion. Again, simple harmonic motion only really deals with the amplitude and possibly the period, right, or the frequency, that W value getting us to those two things. Again, we're not shifting it. That's why we call it simple. We're not shifting left, right, or up or down. I know we've dealt with probably more elaborate things than this before. If you have any questions about simple harmonic motion, make sure you talk to your teacher. Otherwise, have a great day.